have slides?
Huh?
We have slides?
No.
Oh.
Just rolled the thing up.
Projector's on, I think.
I hate slides. Hate them.
Forget who it was, but someone of importance once said that if you're briefing the President of the United States and you can't explain it without slides, you should not be briefing the President of the United States.
I like that. All right. All right, this is a network that we had last week. And it is 4.4. So, if you remember last week, we were talking about by observation, can we compute the shortest paths in this network? And we took a stab at a few and figured out the shortest path from A to E was via B and C, right, for a path of 7 last week. So today I wanted to come up with an algorithm that could actually do that. So notice still the algorithm takes an entire picture of the network, right? So where we haven't got to the point where we can do this distributed, but we have a view of the network. And let's say that we were writing an algorithm and we could pull in each, as we discover nodes, we can pull in their information and then compute, right? So how, if we were starting at A and we want to find the source tree for all of A to every different node, and find what the shortest path in this network is, how do we do that? Well, we have some information. A to itself is 0, right? And A also knows that it is connected to, so this is a net. A also knows that it's connected to B, E, and that's it, right? B and E. Now because A is itself and it owns its links, it also knows what the cost for each of those links. A is the owner of cost. So and the first round knows that to get to B is 4, and to get to E is 10. And this is all that it knows. So if we had a picture of the network and we were going to design an algorithm, how would we go about finding where all the question marks are? So from A to B, C, D, E, F, G, and H. We have a picture of the network, so we know those are all our destinations. What's our algorithm? How do we go about it?
Ask E and ask B.
Yeah, so if we could ask E and ask B their information, but I would propose that let's just ask B. And the reason we're going to ask B is because B is the shortest path, right? And remember that all subpaths of a shortest path are also shortest paths, right? There cannot be, because A has 2 links, 10 and 4, B, that has to be part of a shortest path, because the shortest path is to B, right? So what we're going to do is we are going to try to find a different color marker. Nope, just red today. Ooh, purple, maybe. So we are going to go to B, so here, and we're also going to save this. It has to be a shortest path, because it's the only way there, right? So B becomes permanently 4, right? Now, we can use the property of optimality, which is all subpaths of a shortest path are all in themselves a shortest path. So we can use the property of optimality of B. The next hop from B is likely to be a shortest path, right? So B crawls out, and what do we gather? So for right now, we know that E is 10, right? From our initialization. So from B, what do we get?
C.
We get to C at what?
6.
At 6, right? I'm going to do this in a column. So this is our initial state, and so C is at 6. Where else can we get to?
G.
We can get to G at 7, right? What else? We can get to E at 8. Right? What else?
7.
Huh?
F at 7.
And we can get to F at 7. So B only connects to C, E, F, and G, right? So what do we do now?
Take the shortest path.
Huh? Take the shortest path. That is C, right? So this 6 becomes permanent, right? And then we move on to C. And what do we do? What do we learn? So we can now get to D for the first time, right? At 6 plus 2, so 8. And we can get to E, right, at 7. And we can get to H for the first time at 9. And that's it, because otherwise we go back to B. Can't go back to B because B is fixed, right? So now we go to where? We go to E. And E becomes fixed at 7. Right? And then we continue on processing. Now, since we have an entire picture of the network to begin with, because we're the network gods in this scenario, right? When all of these become fixed for every endpoint, we now have the shortest path for everyone. Now we got a little bit more information than we needed, right? So we have actually the shortest path, all we need is a forwarding table, right? And in this case, forwarding table is really just forward to B. From A.
Doesn't it depend on where you're trying to get to though? Or are you just trying to find the shortest path between all nodes?
Yeah, you're trying to find the shortest path from A, and then all, if you wanted to do the other ones, you would do it, right? But there's a property called optimality. So if you find a shortest path from A to E, which was our example last week, right? This is our shortest path to A to E. Every path in there is also a shortest path. So that means A to B is the shortest path, A to C via B is the shortest path, and so on and so forth. It has to be. Otherwise, you can just observe and say, hey, I would have took a different path to get there.
So would you have to do this for each node being the starting point?
Yes, you would have to do this for each node to be the starting point. So what are some of our problems?
It's going to take a long time.
It's going
to that.
It's going to take a long time. It doesn't scale linearly. It's super linear, right? Often, if you guys go do graphs in any of your career, many graph computations are NP hard or if not complete, right? And then even estimating graphs are often NQ, just to get the estimate, right? So this scales at super linear. There's no if or ands or buts about it, right? So doubling the size of the network is way more than double the computation. Right, and it also takes a full view of the network, right? We have to have an architecture view of the network and what all of our endpoints are, just to start. Which is not often the case in the internet, right? So, let's move on to a different one. I'm going to make a simpler network for this, because otherwise we'll spend this class and the next class doing this. Let's make a very simple network. So this is called Dijkstra's algorithm. It was actually in 1969, a guy figured this out. But it takes a picture of the whole network, right?
The one that we just did is called Dijkstra's?
Yeah.
Is that OSPF?
Huh?
Is that OSPF?
No, but OSPF does use Dijkstra, but it uses link state to start, and we'll get to that today. Okay, let's have a much simpler network of A, B, C, and D. Three, 7, and 6. All right, we have another simple network. We could run Dijkstra if we had that. But this time we're going to do this as if you are a node in place on this network and you have no idea what the network looks like. So what we're going to do this time is, and this is called distance vector. What we're going to do this time is every node is going to share its current table. So remember, in our init process, because A over here, A owns the links between E and B, it knows the cost, right? And so it can send those costs to its neighbors. Ironically, in this first process, B and E would also know that, right? But you get to get a good thought process. Let's just start with A. A sends the cost to B and E. Right? Or in this case, A is going to send its cost to B and D because those are its only local links. And then D is going to use those costs to figure out other information, use its own information, because it will have information of D to C, and B would have information also of C and D, right? And we'll start adding that information together. So in round one, now I'm going to put A, B, C, and D up there, but recognize that you don't know the entire picture of the network, so you don't know what all the nodes are. So every time you encounter a new endpoint, right, you just simply add that to your table, right? But so let's have A, B, C, and D. So, and this is going to be A's table. And let's look at B's table. We'll also have A, B, C, and D. So init, A knows what? A knows itself as 0. And B knows itself as 0. Now to start the algorithm, remember I'm going to have B share something with A that it already knows, right? This way the algorithm just repeats itself over and over again. So B is going to send its information to A. So B sends its information, which is, hey, I'm B, and the cost to myself is 0. A would receive that. And what will we learn, right? So B would now be 0 plus 3. We're doing this backwards, right? So the cost of B is 3, right? And we don't learn anything else, because we're just going to set these all at infinity. And in reality, you set them at 16, but we're going to set them at infinity for the concept of it. So in round one, B sends that to it. Now, in round one, every other node has also done this. So in round one, B also received its initial packet, which was, hey, I'm C, and I have a cost of 0 to myself, and B knows the length is 6, right? So in that, right, we'll learn this, right? C would become 6, and D would become 3. Right, and then D would also have sent a packet about itself in round one, and A would add 7 to that, and so we would learn 7. Right? Now in round two, they just send the same tables again. Right? But they're updated stamps, right? So A is never going to receive anything from C. It's only going to receive things from B and D, right? But B and D would, in round two, would have learned of C already. And so they would pass that information on to A, right? So B would send a thing to 6 to C, but it would be 6 plus 3, so this would be 9, and I don't know why I wrote that 7, that's supposed to be 3. This was supposed to be 7, right? And so, and then in round 3, right, because there's only a 4-node network where it can't possibly gain any more information past round 3, right, we would learn the entire topology. And everything would converge. And we would see, like, hey, because these things are coming out periodically, right, we would see that we're keep getting the packets and nothing's changing. And we would learn that the best route to D is not be directly over this link of 7, it would be directly a link of 6, because it would get lower and then it would never get any lower. And we have converged. So what are the benefits of this algorithm?
Everyone learns everything at the same speed.
Everything learns at the same speed, right? The calculations for the network are actually sublinear. So you can get to a ridiculously large network because assuming that there are more than one branch off each router, otherwise it's just a bridge, right? Then every time you go out all those forks, right, you're going out something greater than 2, probably. At least 2, but it's probably something greater than 2. Right, so we're learning something sublinearly. Is there any problems?
Well, you mentioned that it stops eventually, but if the network's changed, it wouldn't stop.
Yeah, so it actually turns out this is great for adding, right? Because every time you add a network, a node on the network, and when we say nodes, we're talking about routers in this case, right? So you add a router to the network, right? It just starts the algorithm, right? It says, hey, I'm Jason, I'm new to the network, the route to myself is 0, right? And then it just propagates through the internet. It can propagate through the whole internet without much problem. It turns out, you know, even if there's only 2 connections, right? How many rounds do you have to do before you get the entire internet? On average, right? So if there's a billion things, there's only a billion IP addresses. There's actually 4 billion IP addresses, but there's only about a billion that are usable. So that means you gotta go out 31 times. And that was if there's only 2, right? You start putting 3, 4, 5 different ports on each of the routers, right? It's gonna be much less than that. And in like the original RIP protocol, which used this distance vector, the number was 16. It went out 16 times, and then it would just stop at 16. But there is a major problem with it. And the problem isn't adding things to the network, it's subtracting things to the network. So remember, A is not communicating with anybody but its neighbors. And the neighbors are only keeping a state of its current table and then propagating that out. So in round 1, A introduces itself to B as itself, right? And the distance to itself is 0. And B's like, okay, well, I have an own link with you, and I just add 3 to that, right? And then we eventually converge, right? And so we would come up with this table that looked, from B's perspective, it would be like, so B's table would look like A is forwarded on to A at a cost of 3, and C is forwarded on to D at a cost of 5, and D is forwarded on to D at a cost of 3, right? And then of course you have the trivial case of itself, B to B to 0, right? So that after everything converged, we would learn this information, right? We'd come to the steady state. What happens if A goes down? A goes down, right? And we have to repeat this process every once in a while to find dead nodes. The problem is now, B would have this table, but then it would say, oh, A is down, because that link is dead, right? So A would become infinity. A to A is no longer good. But what does C send B?
It's destined for A.
Well, not only that, it says, hey C, or hey B, I have a route to A of 9, right? So then it would go, hey, C, A goes to C at a cost of 9. Well, what is happening here now is, of course, C's route to 9 is also through B, right? And so as we forward these packets back and forth, right, we're going to add 6 each time. Because B will keep trying to find a route to A, even though A is dead on its own link. Well, then you can say, oh, well, it's its own link, right? We could just put a special case in there that says, hey, if it's my own link, clearly you can't go through me to get to A. I need to find another route to A. The problem is then we can just do the same problem, just extend it out one further. Right? Suppose there was an E over here connected to C, right? Then we could, if we just said, then, right, we'd end up with the loop right here, right? And then C would clearly have no idea that any link's down at that point. So there can't be any special case. So what they do to solve this in real world scenarios is they put a maximum number of hops. Right? If it is further than 16 away in the RIP protocol anyway, it's actually a dead link and discard it. The problem is that now we're having to converge through the internet, right? We're gonna have to pass all these packets through the internet over and over and over again, at least 16 times in RIP, to find out A is dead. Well, there's a lot of routers in the internet, right, that might not be, one, it's not fast, right, because let's say we have A and then we have like Z over on the other end of the internet, right? Those packets have to be propagated all the way through. And then we'll have to do that 16 times. And so even though the internet can certainly handle that amount of packets, and we're not flooding it with anything, the convergence is slow. It's awful to figure out that something's left the network. And the reason is because we are only using stateful information, right? We send each of those individual, they're unlike Dijkstra where we were keeping track of everything, right? And had a big picture of the network at all times. Now we've gotten rid of that big picture network for simplicity, but that means that we can't detect loops anymore. And we run it. Huh?
So you merge them.
So we're going to merge them, sort of. Let's move to the next one. So, distance vector, very efficient, right? Sublinear computation, but is slow to converge. Errors in the network are propagated out for a long time, right? You actually have essentially a timeout, and just the timeout is number of hops for RIP, but it could be just a maximum cost, whatever you want to do, just depending on your implementation. But it's a timeout. Timeouts are usually not good, right? So we're going to try to do something else. And by the way, that loop is called a, not that it's going to be on any test or anything, but the loop is called a count to infinity problem. Because it just, huh?
Caltech infinity problem?
Count to infinity.
Okay.
Count to infinity problem, sorry. Because is simply, even if the cost is 1, right, it just keeps incrementing 1, and they keep telling each other I have a route back and forth. So we're going to diverge a little bit to talk this is pretty simple, but we're going to need it in the next algorithm. And this is the concept of flooding. So flooding is much like we talked about broadcast in the network layer, or in the data link layer. So flooding is the idea of trying to pass a packet to every node in the network. So if A wanted to flood, what would be a good algorithm to do that? And remember, we have loops in here, so we don't want to have packet storms. So what do? I want to send information. A wants to send information to every node in the network.
Start with shortest path and work your way back.
Yeah. So what you do is A would send a message, broadcast message. I mean that in very light terms. A is going to send a broadcast message to E and B. And what E and B are going to do is they are going to forward it on every port they didn't receive it from. And they are also going to remember that they flooded this message. This is to prevent storms. Right? Because if you didn't remember, A would flood to B, B would flood to E, and E would flood back to A. So the algorithm is simple. A sends a message to all of its direct connected ports. The routers on the end of those will duplicate the message for all of the ports except for the ones that it received it from. So it doesn't reflect it back to A. And it remembers which one remembers the flood message. This does not prevent, if you notice that if we run through this, this does not prevent the message from arriving at a router more than once, right? But it does prevent it from being circularly repeated. So A sends a message to B, flood message to B, and flood message to E, they're both connected. E duplicates that. Oh, let's do it B first. B duplicates that in round 2 and would flood it to C, would also flood it to E, so E receives it the second time, and flood it to G. Right? E, and also in round 2, would send it to B. The packets would actually pass each other in transit. Send it to F, and send it to D, and send it to C. So C would have received it twice also. And then in C, round 3, B, oh, we forgot this route. Now notice that in round 3, B is already sent it out every single port, right? And because of the anti-reflection rule and the remembering rule, we can't get it back. So B would be done, even though it's sent it, E has received it twice. And then, and so in round 3, G would send it to F. C would send it to D. E would send, no, E would not send it to D because it has, and then we would get it here. So while a bunch of different routers would receive it a couple times or more than one time, right, it prevents the packet storms, right? So we do have a way to flood message in a network. How can we use that to a benefit for routing?
Can we have it if one router, if one node realizes that another node is dead, to flood a message to let everybody else know that's dead?
Oh yeah, we could do that. Yes. What else could we do? What about flood or links? What if we say, hey, what if A, instead of just saying this is a blank flood packet, what if the payload for this packet was, hey, I'm A, and I have a link to B at 4 and to E at 10. A could communicate that to every node in the network, right, via flood. So C could also communicate that it has a link to H at 3, to B at 2, to E at 1, and D at 2. And flood that to every node in the network. So that means that every node in the network, in this case nodes are routers, because nobody else is really going to care, So every router in the network can receive every other router's local connections. Could we do something with that? Oh yes. We could build a picture of the network. Right? So you would learn, hey, there's A in all its connections. So you learn two useful pieces of information. Like let's say I'm Z, I'm out on the end of the network, right? I receive a packet from A, says, hey, I'm a router, I'm connected to E and B, and my links are 4 and 10. That's a part of a network, right? And eventually, if I receive everything in the network, then I would eventually be able to see that there is a network topology that includes all of these nodes. I don't actually have to build a physical graph out of it, I just need to keep the numbers. And then if I just keep the numbers, then I can use Dijkstra to compute a path. What's the advantages to this?
You just merged both.
We have merged both, right? So we have, we now have built an entire picture of the network, right? So there's definite disadvantages. We're using Dijkstra, which is super linear, and we're making the routers do all these computations, right? The other disadvantage is that we're no longer taking advantage of, full advantage of shortest paths, right? Because we're duplicating, there's many nodes duplicating the same computations, right? But at the same time, just like in any distributed problem, right, if one of the distributed problems are going to fail, right, it would be nice to have backups. And this essentially allows us to have all the computations, even though we're doing some computations in duplicate, right, that means that if a node fails, then we can converge rapidly. And we can converge rapidly because A would quit sending packets if it died. It would no longer be sending out, hey, I'm A, and these are my links, right? And it would also be like, there's two different types of failures, right? There's a link failure, like the port goes down, so the network card dies on a router, right? The router's still running, it's just the network card dies, or somebody cut a cable, right? Somebody was digging a hole in a place they weren't supposed to dig, right? And cuts a cable. Well, if the router's still alive, it's just the link that's dead, right? So in that case, A would still be sending packets, but now it might be sending, hey, I'm A, I have a link to E at 10. And it's no longer communicating B because the construction guys cut the cable. Or you could have a link failure, or a node failure, right? Which means the router itself dies, and then it's no longer sending those packets at all. But either way, the network is learning the state of A rapidly. We're no longer trying to count down and figure out, hey, run into a timeout value and say that, hey, A is dead. We can now just compute it. So, benefits are we converge rapidly. We rapidly learn that something has died in the network. While the computation is super linear for Dijkstra, we get near distance vector, at least learning of routes to the internet. The problem is that there's a certain point where it won't scale. Right? We can keep building a network big enough to where we just overwhelm the routers. Remember, graph computations are ugly. So at a certain point where it's just going to be ugly, right? Because notice as we're going through Dijkstra on this graph, we covered every single link. So from graph perspective, we hit every edge in the network. Well, if we have a network with 100,000 nodes, right, then there's clearly more than 100,000 edges. Right, and so the computation becomes very, very large. So what are some ideas to get around that? So the link state is actually open shortest path first. There's some other implementation things that are in there, but the idea of this link state routing is the basis for OSPF and some other like more local protocols. But it doesn't scale all the way to the internet.
So we learned about BGP then?
Yes, we are.
What was that?
We're going to learn about Border Gateway Protocol. So, before we go on to something like that, right? So far, when we're computing all these, whether we're computing a distance vector or we're computing it in Dijkstra or the combined version of Dijkstra, which is link state routing, we have, every time we reached a tie, where the cost was the same, we just arbitrarily picked one. So if we do that, then we are wasting bandwidth, clearly, right? So there ought to be a way that at times we reach a tie that we can use those links that are tied. So if you consider when we were arbitrarily picking a tie, the reason that we were arbitrarily picking a tie is because we wanted a source tree. We wanted a clean tree where all nodes on the tree had one path to reach there. But in order to save bandwidth, or I guess more efficiently utilize bandwidth, right, we would like for those equal cost paths to actually both be used. So what do we do? So we would like to, instead of so from like a Dijkstra point of view, we have this algorithm, right, that we can actually compute down through here. And remember, Dijkstra, we just went to the shortest path and we computed the shortest path, and we computed the shortest path, computed. And then if we reach the tie, we just arbitrarily break the tie and move to one and compute, right? But of course, that means that the tables are incomplete from a bandwidth point of view. So could we design an algorithm that actually utilizes those and remember them?
Make them equal. If you make them equal, so they can pick either or, depending on.
Yeah, well, so yes, but from an algorithmic point of view, right, unless you're going to like span off another process, right, where we're now like duplicating stuff, right, we would like just a linear process to get through and converge it. And actually the answer comes up very simple, right, is we do Dijkstra just like we did last time, except for this time we just remember the set of next hops. So do Dijkstra last time, but remember when we did Dijkstra, right, it was we just remembered that one. So this time we're going to do Dijkstra, but we just remember every time we run into something that's even, we remember all three, or four, or two, or whatever we did to break the tie. Just remember those, and that's all you have to do. You don't have to And essentially what you're gonna do then is you're going to move off to, I can't remember where there was a tie in this one. I have too many lines in there. Anyway, you reach the tie, you remember up next next stops, right? And since you're branching off at shortest path, then that is also a shortest path because we were starting from that point of view anyway. And then you can forward packets to as many as you want, right? But then the question is, how do we forward packets? How do we choose which ones to forward?
Just switch on.
Huh?
Do we just switch on?
So first idea, let's just do round robin. So let's say that we had, to get to Z, we had A, B, C, and D that were all equal paths to Z. Right? A, B, C, and D are all equal paths. So we could just do round robin. We encounter a packet and we send it to A. Then we encounter a packet, then we send it to B. We encounter a packet, we send it to C, D, and then we start over at A. Right? Definitely utilizing bandwidth well. Is there any problems with that?
Basically guarantees your packets are going to be out of order.
It almost guarantees your packets are going to be out of order. Why? They're all equal costs. Why?
Because they may be equal cost, but the distance or delay.
Correct. Correct. Equal cost does not mean time. Time is certainly a part of equal cost, right? But it doesn't mean time. So we might receive packets out of order, right? Even if they were relatively close to the same time, and we received them in order, which in the case of the 4 different branches is unlikely, but let's say that we did receive them in order, right? They're no longer, for sure, going to no longer be evenly spaced. So this is going to become super important when we get to the transport protocol, is right, we would like our packets to be evenly spaced. We are going to use that even spacing in packets to create a counter in the network, an actual clock. It's called an ACT clock. And we're going to use that to do flow control. How do we know when to send the next packet and, and get through the network without, jamming on top of each other and something being dropped at the router? And the answer is the ACT clock, right? But the problem with what we just talked about for round robin was now we'll have jitter. Our ACT clock will be all over the map, right? Because we'll have some packets that are really close together, some packets that are very far apart, at least, if not out of order. And so, and when we get to the transport discussion, right, out of order packets in the transport, a lot of times, at least in very simple transports, means you drop them. Right, you look for the next sequence number, and if you get something that's out of order, you drop it. Right, so it could be devastating. Of course, we're going to build more, like the rest of the class. We'll start out simple, and we'll build more complex transport protocols that can deal with out of order packets and stuff, right? But that ACT clock is still going to be important, right? So is there a better way?
Pick a path for the entire packet or something, framing it, I don't know.
So you pick it, well, that's the right answer. You just pick the wrong unit, right? You pick a single path for each flow. So if A is talking to Z, right, then A is bad because we used A, B, C, and D. But okay, F is talking to Z, and it goes through A, B, C, or D. Once it starts talking, the router that is going to forward that off, F, remembers, for this communication, I am going to use A. And it just remembers that communication goes through that path. right? And then the next communication that comes through, right, that hits F, because remember, the F, if A, B, C, and D is talking here, there has to be a single point for all these to be equal, right? So, and they're all talking. So the next one, F would say, hey, I'm going to give you B. And then the next one, I'll give you C. This does not utilize bandwidth as well, right? Because the first one might be heavily data communicative. So it's moving a lot of information across the wire, right? And then the next random one is really light, right? And so maybe it's just a heartbeat, and the next one, you know, is something different. So you'll get uneven utilization of bandwidth, but in practice it evens out pretty well, right? Because it's not we're not picking one communication. We're picking, you know, we're not picking 4 communications over 4 lines. We're picking probably thousands of communications, if not millions, over 4 lines. So they're likely to be kind of evened out. And that reduces the jitter and allows us to use an AT clock, which is going to be really important when we get to transport. Is there any questions for today? Nothing? All right. So we still have to talk about link state protocol not scaling to the internet, right? So it turns out we're going to use link state and distance vector together, right? And we're also going to put a lot more complicated information in there, and then we're going to call that border gateway protocol, because there'll be all sorts of weird stuff for costs between, like, so right now we've always had like a packet is a packet, and it only matters where it came from and where it's going. But it turns out cost might be different versus where it came from and where it's going. So border gateway protocol needs to be able to take that account. So if, for instance, right, if you are on AT&T, right, and you're streaming stuff from DirecTV, and the same company owns both of them, then the costs for those networks are probably really low, versus you streaming something, you're on AT&T and you're streaming something from Comcast, right, where the cost might be really high, right? So then we're going to have to pick, like, based on what contents and different agreements that companies have together, and be able to construct a protocol out of that. And we will lightly touch on border gateway protocol, lightly. But it'll give you an idea. The idea is to get the basics, not to actually implement it, right? The idea is to get the basic, to know what the limitations are and why things are the way they are. Okay.